Hi, I'm Iyad. In this video, part 1, we're gonna understand the limit of a function and its definition through some examples and illustration that I've prepared for you beforehand. Let's start with the first point. To understand what the limit of a function is, let's take this example and let me ask you what is f of 1. If we plug 1 here, we will get 1 minus 3 minus 18 plus 20 over 1 minus 1, and you'll find it to be 0 over 0, which is, I can hear some of you saying this is undefined, but actually this is inaccurate. This is an indeterminate form, which means that it could be any number, 0, 3, -4, and it could also be undefined, which means that it goes to infinity. So what is the right answer? In order to know the answer, let's see together the behavior of this function around this critical value of 1. For this purpose, I calculated the values of f of x in the range from 0 to 2 using Microsoft Excel. We notice that as x approaches 1 from both sides, y approaches 21 from here and here, which suggests that f of 1 equals 21. But unfortunately, we cannot write this because at exactly x equals 1, the function is undefined. And as you see here, Microsoft Excel gives an error saying that this is division by 0. So let me put it like this, f of 1 is 21 wannabe. And here comes the notation of the limit, which describes this behavior. So we write the limit of f of x as x approaches 1 equals 21. And now let's try to write a definition of the limit. But before that, I'd like you to bear in mind that the way we find the limits in practice is of course not like that using datasheet. It's rather based on algebraic simplification as follows. By factoring the numerator, which is a polynomial of third degree, it's simplified into x minus 1 times this. And here we notice that we can cancel x minus 1 from here with x minus 1 from here. So it becomes negative x squared plus 2x plus 20. And by completing it to a perfect square, it becomes this. And here at this point, we can calculate the limit of the function as x approaches 1 by putting x equals 1 here, which gives y equals 21. And by the way, this method is useful in similar cases where we have an indeterminate form. As for the last formula, it's useful to know how the graph of the function looks like. This is the equation of a parabola whose summit is 121. And as you see here, this is the summit, but I put an empty circle, a little circle here, which signifies that the function is undefined at x equals 1. Well, basing on our example, it sounds acceptable to define the limit as follows. If x is close enough to a, as we see here, y gets close to L, and the closer x gets to a, the closer y gets to L. And here, it's enough to keep x not more than 0.01 distant from a for y to be at most 0.0001 from L, which is 21 in this case. This was simply the informal definition of the limit. However, unfortunately, this definition is not solid as it seems to be. Let's, for instance, take this function, and let's look at the behavior of this function when x gets close to 0. Which means we would like to calculate the limit of f of x as x approaches 0. So here we have a equals 0. And we're seeking the limit L. We see that as x approaches 0 until a pretty small number, 0.001, y approaches the number 1. So it seems to be that the limit of y as x approaches 0 is 1, according to this definition. So is it 1? In fact, it's not, and the limit is not 1, but 0. Simply because if you put x here, you will get here 0 over 0 plus 1, which is 0. So we've got deceived by the data here. In fact, here we need to get even closer to 0 than 0.001. Now we can see that the function doesn't stop at 1 as x decreases, but it continues to decrease towards 0. So now we can see that the real limit is 0, not 1. So the problem with this definition is that this phrase, close enough, is very relative and is to mathematics ambiguous, because what was enough in the first example is not enough in the second one. As you see in the first example, we got no more than 0.01 from A, and it was pretty enough for y to be enclosed in a very little interval around the limit L. While in the second example, even 0.001 from A, which is 0, wasn't enough. So we've got to add a condition to the informal definition, which is it's possible to get closer to the limit L on the y-axis as much as we wish and never go beyond certain distance, no matter how close x gets to A. So let's discuss our first guess, which turned to be wrong, which was the limit of f of x as x approaches 0 is 1. This one. And let's note that we have here a equals 0, which is this number. While this is the alleged limit, and let's call it L prime. Now, according to this condition, we may wish to get close to L prime on y-axis within the distance of just 0.01. So here, if we take a distance of 0.01, we will end up here. However, as we get closer on the x-axis to A, we see that y fails to keep within this distance. As you see, all these values are beyond this limit, which explains why the value 1 is not the limit. Now let's sum it up and reformulate it. So first we had this informal definition, then we added this condition, and this sums up to this definition. Let's say here is x and here is y, and x approaches A and y approaches the limit L. So the definition says for whatever distance epsilon from the limit L, let's say here, we can find a corresponding distance delta, small Greek letter delta, from A, which is here, such that for all values of x within the distance delta, y is still within the distance epsilon from L. And in the language of mathematics, it's written for every positive number epsilon, and y is positive because it's a distance, or it means that it's from both directions, from both sides, left and right. There exists delta, also positive, such that the absolute difference between x and A is less than delta, implies the absolute difference between y and L is less than epsilon. And that's it. To apply this definition on an example, let's consider this function. F of x equals len of x minus len of 3 plus 1. And of course, len is the natural logarithm, which is the logarithm for the base e. But first, I'd like you to know that the definition of the limit is not restricted to the case where f is not defined at x equals a, but it's generalized to include all the values of x in the definition set of the function. Like this value, a equals 3, we can calculate the limit. And for such value, where a belongs to the definition set of the function, we have the limit of f of x as x approaches a is simply the value of the function at this value of x. For example, here, the limit of the function as x approaches 3 is f of 3, as you can see here. And now the task is to apply the definition on this case. For example, let's take epsilon equals half, and of course we can choose it much smaller, as much as you like, but I chose it to be 0.5 just to be visible on the graph. Now we should find the value of delta. We may do that simply by finding the corresponding values of x for the edges of this interval, L minus epsilon, L plus epsilon, which is from 0.5 to 1.5. We see that the corresponding value of x here is this one, and here it's this one. And they are different. This is smaller than this. So which one is suitable to be taken as delta? If we take the large one here, we should take similar distance from the other side, which will end up somewhere here. But here there's a problem, because for any x, here it will have its corresponding value of y beyond this interval. So it doesn't work. This is why we should take the smaller value, which is this one. And now, whatever x is in this range from a minus delta to a plus delta, the corresponding value on y will be inside this range. And the remaining task now is to find this value. Unfortunately, this is not hard. Simply, we have here y equals 0.5. So let's put it here. So we have 0.5 equals this, which implies that ln of x equals 0.5 plus ln of 3 minus 1, which I found to be approximately 0.6, which implies that x is the inverse function of this function, which is the exponential. So it's the exponential of 0.6, which I found to be approximately 1.82. So here we have this x is 1.82, and delta, if we want to calculate delta, it's the difference between a and this x. So it's 3 minus 1.82 equals 1.18. And I want you to know that you can take any value for deltas which is smaller than this number. So the matching interval on the y-axis is maintained always to be inside this interval of L minus epsilon, L plus epsilon. So why don't we take an easy number such as 1? So let's take delta to be 1. And the interval is gonna be from 2 to 4. And as you notice, we still have the corresponding interval on the y-axis is included inside this interval. And finally, we write for every x where x minus a, which is 3, is less than 1, which is delta, implies that y minus the limit, which is 1 here, is less than epsilon. And this guarantees that the limit of f of x as x approaches 3 is equal to 1. I hope this video was useful. If yes, please like it and you may subscribe to my channel. Thank you for watching.